All right, so I guess I better get started here. So this is CS 110, I think, right? Okay. So I'm Kenrick Mock, and for the next 5 weeks, you get the intense Java programming class. So on Blackboard is the syllabus materials, and so what I wanted to do is start by going over that. Does everyone have access to Blackboard? No? Is there anyone that doesn't have access? Okay, so anyway, if there are any problems, let me know about getting online. So I'm assuming you can all log in, and what we'll do with the class is like the second half of the class is going to be like on computers activities. Okay, so on Blackboard, I've got the syllabus up here, so let's start there. So obviously, you know, we're here in this room, and there's my email. My office hours are basically right after this class, with the exception of today. I had something had to be at 2, so I won't be around after class today. But if you have questions in that second half where we're going to do the on-computer stuff, I should be able to help you there because it's a pretty short exercise for today. Let's see. So you need to be able to get online. Here I also assume you have some basic knowledge of algebra. There's not anything really complicated. Like we'll do like exponents and that's about it. In the past, we had some trig functions like sines and cosines, but you didn't really have to know about them. You just take the sign and you get whatever number you get out. So there's not tons of math, but you do need to be able to think logically, and so that's probably the main kind of math part is just have logical thinking. The required book is, does anyone have the book? Is this Introduction to Programming? Is this book with the red bridge on it? There's actually a newer edition out, and you could actually use the new edition, this edition, or an older edition. It really doesn't matter. If you go 2 editions back, that's getting a little too old because the language changed a little bit. But you can use any kind of recent edition of the book, and it should be fine. I don't follow the book like religiously, and so kind of my philosophy is I'll teach a little bit differently than the book, and so you have kind of 2 different perspectives on the material. So some of you might learn better reading the book, and others of you might learn better, listening in class. And so whatever works for you, I don't want them to be like the same identical thing. It just one me talking and one you reading. Let's see. The book has this thing. If you get a recent edition, there's this thing, My Programming Lab. That's not required. That's like a bonus kind of material that comes with the book. And basically, if you feel like you need more practice or you're kind of getting stuck on certain things, then that's like a nice activity to maybe kind of get you moving if you're getting stuck. All right, so what's covered in here? So most of you are not computer science majors. I did see there were a couple in here. But most of you, I know, are doing the BS in something, biology or chemistry or whatever, geology, and use this to satisfy your programming requirement. And so you'll see a little later on, I'm trying to take that into account in terms of how the course is structured. But the goal is to introduce you to fundamentals of computer programming and problem solving. In this case, we're using the Java language. Once you learn something like Java, it becomes pretty easy to learn lots of other languages. So like if you ever had to do stuff in Visual Basic or C++ or something, it's not too much of a leap from Java to the others. So it provides like a pretty good foundation to learn other languages if needed. And even if most of you are not being computer scientists, there's a pretty good chance you'll at least interact with a computer scientist on some problem or do some kind of programming in support of whatever you're doing. So if you're doing something in mapping and GIS, there might be a little bits of programming you have to do to modify it to your situation. If you're going to grad school, most grad students do have to do some little bits of programming to analyze their data or format their data or something. So there's a decent chance some of this will come back to haunt you at some point. Let's see. So here we'll talk about types, operators, classes, objects, inheritance, iterative execution, variables, parameters. So all this stuff probably doesn't make too much sense right now, but hopefully it will by the time we get to the end of class. And then we have these outcomes that our goal is students can do these if you finish everything in the class, is be able to modify examples, write programs that do text and graphics, design code for classes, identify types, use conditional and iterative execution, write methods, use arrays and file I/O, and then a little bit on recursion. Okay, so the way I'm organizing the class is a little unusual, so I'll get to that when we get to the grading part down here. But as far as the actual mechanics of the class, I'll lecture for a little while, like 45 minutes to maybe an hour. And then after that, I'll have like this sort of hands-on drill. I call them drills. So they're pretty short. I shouldn't say really short. They're moderately short to sometimes a little bit longer programming exercises. Where if you like knew everything you had to do, then like just typing it in would take you like 5 minutes. But if you're figuring stuff out along the way, it's going to take a little longer. But the goal is they're hopefully of a length where you should finish them, somewhere between like 15 minutes if you're really on target to an hour if you have to still figure things out. That's the goal. Sometimes people might not finish in the hour, which is okay. But I'd be around basically to help you out. And you'll see there are certain things that can trip you up that are really tiny. And so you're missing a comma in one place, or you put a colon or something where it should be a semicolon. In English, that really doesn't matter too much, but with your computer program, it just won't work at all if you have something just the tiniest bit out of place. So you have to really pay attention to detail, or things can go south really quickly. So that's one of the goals for this hands-on thing, is if something is wrong, I can come and say, oh, you need to put a semicolon right there, and then everything will work. So hopefully I can fix those things and you won't make those mistakes in the future, and you don't get frustrated for hours trying to figure out what's wrong when it's just one semicolon. Let's see, so here we're using Java. One nice thing about Java, it's a free language. You can download it and use it on your own computers. So you can run it pretty easily on Macs or PCs or Linux machines or whatever else you might have. And actually I haven't checked to make sure everything's installed here, but I assume it's installed here. We'll see, I guess, in a little while. The software should also be installed in the other engineering labs, so like the Atrium lab, for example, or the ones upstairs in like 218. So you should be able to use those machines if you just need a place to work. There's also a lab in NSB 204, the Natural Sciences building, and so the one right next to us here, between here and SSB. So there's a lab there, and you have to use your Wolf card to swipe and get in, but that's another lab you could use. Let's see, we might have like a tutor. I'm not sure yet. We haven't found. There was a guy who was going to do it, but then he got a real job, internship job. So hopefully we'll have a person that can be a tutor in the lab, but we'll see. I plan to give you 4 homework assignments, and then each assignment has multiple programs to write. The first one has like a bunch of short programs to write, and they get a little bit longer as you go through the class. And then I'd like you to turn them in through Blackboard, compressed in a zip file. Maybe I'll go through that a little bit later today. And you'll see that the assignments, they don't have like a fixed due date, but they're kind of tied with these exams. And so you should complete them kind of around the same time as the exam, which we'll talk about here in a second. And then the grading is also a little different. So normally I would just, you do submit your assignment and you just get whatever score you got, and then you move on to the next assignment. In this case, I'm kind of making you like redo your assignments until they work. So I'll say more about that in a second too. Let's see, I already mentioned we're going to have these sort of drills at the second hour of the class. You don't have to send those in to me or anything. Basically, what I'd like you to do is you work on it, and then just like raise your hand when you've got it finished, or if you have questions, and I'll just come and mark off that you finished it. If you complete them at home or something, or you want to take longer than the hour, you could email it to me or just show it to me the next class or something. So either way, just some way I get to see that it's working and can mark you off. Okay, so here I'm using this kind of weird grading policy, and so rather than just like get a score on all your assignments and exams and whatever 90 and up's an A and 80 to 90 is a B, so I'm trying this thing where I want you to complete sort of everything in one topic area, and if you complete all the stuff in that area, then like you get a D, and then if you complete everything in the next area, then you're guaranteed to get like a C. So that's the idea. So basically if you do nothing, then you'll get an F, or maybe you get a no basis grade, but you wouldn't get a grade really if you do nothing. But if you do just the first homework, but then here when I say just the first homework, I mean you have to get them all working correctly. That's where I was saying I'm not just give you a grade and that's what you get. So if like parts of them work, but not everything, then I come back and tell you have to redo these parts because they're not working correctly. So you finish the first homework and the first 7 drills. Those are the things in class. And the first exam, and these exams are going to be pretty short exams, like 30 minutes maybe, and they're going to cover like fundamental stuff. Like sometimes you have exams where you get these really kind of difficult questions, and so I'm not going to say the exams are easy, but they're not going to be like really tricky things. They're like kind of fundamentals. Do you have the basic principles of the stuff that's like in this first 2 weeks, for example? And then the exams are going to work kind of the same way. If you so when you do the exam, if there are questions that you miss, then I'm going to ask you to redo those until you get them right, which hopefully will be this next time, not like multiple times, but if it takes multiple times, then that's what it takes. So if you can do that for the exam one, finish all the drills and the homework, then you're guaranteed to get a D. And then if you wanted to, you could stop. So if that's all you want, you just want to pass the class and that's it, then you could do that and then stop. You don't have to come to class anymore. So in theory, after the first 2 weeks or something, you could do that and then be out of here. But if you don't want a D, if you want to at least get a C, then you have to complete homework 2, and it's the same kind of deal. You have to get everything working. Same for these drills, same for the second exam, and then rework any errors that might have been there. And so basically that's the 3rd week, and the next one's the 4th week, and then this would be like the last week. So the main reason for doing it this way is the class material really kind of builds on itself. So it's if you think of like spelling or something, if you don't know the alphabet, then you can't really spell words. I guess you could kind of just by shapes or something, but you can't do it very well. And then you certainly can't really make very good sentences if you don't know the alphabet. And so it's sort of the same thing here. If this stuff up here, like in this first level, if you didn't really get it very well, in a regular class, we would just keep on going. You just all the topics just keep going. You take the next test of whatever the next material is. But in this particular class, if you didn't really get it too well up here, then when we're talking about like how to write poetry or something down here, then you kind of don't have much chance if you don't understand the part up above. So I've kind of tried to organize it where it hopefully encourages you to learn everything really well for the first sections before you move on to the later ones. And then if you don't make it to the bottom ones, then you still have a chance of getting a B or a C or something, as opposed to getting like a failing grade on the last exam, which would cover a bunch of stuff that you wouldn't know how to do. So that's kind of the idea. I guess we'll see how well it works. So if you have feedback about it, I'd love to hear it. Yeah.
So what if you miss like a drill from the first level? Does that mean you're stuck with E for the entire?
No, and so if you miss one, then you can go back and redo it, and so you don't have to turn in that day. So I'd like you to turn in that day just because I'll be around and that's what everyone else is doing. But if for some reason you miss it or whatever, you can go back and do it later. And it's the same thing for the homework assignments. So that's where I sort of don't have like a strict due date. I would say you should work on the first homework before you take this first exam, because that's the kind of stuff it's going to cover. But you might have to redo some problems or something if they weren't all working. So I'm kind of flexible there. So what I wouldn't like you to do though is wait till the last day of class and have like everything. Like here's all my homework, here's all of the drills. Just from a grading perspective. But so if you could at least kind of distribute stuff throughout the class, that would be great. Let's see. Okay, so the exams, I'm setting up so they take like 30 minutes or less. They're going to be like paper exams. I've had some like on computer exams before, but then I've had cases where like, some people are really fast typers and others are slow. And people sort of get hung up on certain things to make the programs run. So I decided to avoid all that by just making it like kind of a regular paper exam. You can use the computer if you like to access like books or programs you wrote. So like if you bought the ebook or you wrote a bunch of programs, you want to look at them, you don't have to print them all out for the exam. It's open book as well. Let's see. So the only thing I ask you not to do in the exams is I'll have some questions on there where it's like, here's a program, what happens if you ran it? So in that case, I don't let you use a computer to type it in and just run it. Let's see, you have questions, then come by my office, even if it's not the office hours. And then here's just the thing about academic conduct. So you're expected to do all your own work. When we have the drills, you're welcome to work with other students and talk about how to do it. That's totally fine. The only thing with the drills is make sure that you know how it's working. So you can work with someone else and you can turn in basically the same code for your drills, but you should know how it works. So you shouldn't just copy someone else's program and then say, yeah, it works, but not know how it's working. For the homeworks, you should do those on your own. You can talk to other people about strategies, but you shouldn't be like turning in the same code, the same programs. And what else? And then, if something happens, you could get an incomplete, but not if you just fell behind. So it has to be some special circumstances. Okay, so that's the syllabus. The other thing I have on here is this link here for calendars, and here I call them labs, but they're really the drills. So if you go to that link, then here's like a sketch of what I'm thinking we'll cover, although it might change because I was just kind of guessing how fast we would cover things. But over here on the right, I have like PDF files for like notes for the day. So we're going to cover this one today, and we might start a little bit on this one as well. And then here I've got the drills we're going to work on. So the first one is drill 0. I guess I should have started at 1, but there's a reason to start with 0, and that's, you'll see, computer scientists always start counting at 0. So when we start going through things, there's going to be like the 0th item. So I thought I would do the same thing here. So here's the first drill for today, and it should be pretty short. It's basically making sure you know how to type in a program and compile it and run it. And then here's the one for the next day. So if you want to, I'm going to try to get these filled out for the next week pretty soon here. So you could get ahead a little bit if you want to. The other thing I'll put on here is I'm recording the screen on the computer and the audio. So I'll put like the video of what we covered up sometime after class. So if you miss a class or something, you can come back and watch it and see what we talked about. And that could also be useful if you want to review material a second time, then you can check out the video. Okay, so I think And there's some other dates here, last day to drop and get your money back. This last day, whoops, that's weird. This last Monday, there's a class, and that'll just be like kind of slack day. If you need to finish up any drills or redo homeworks or exams or something. Okay. So I posted the first assignment up here already. You can take a look at it. And then here's some links to other stuff. Like if you want to download Java. If you wanted to download Java, you would normally go, let's see here. So Java is owned by Oracle, and you could do, when you click on that link, you would go to like this one over here if you just want the compiler, or this one if you want NetBeans with it. I would say probably if you haven't done this before, I'd probably say get the NetBeans one, because we're going to use that later in the class. So it's pretty big, and it'll take a little while to download. But you can run it on pretty much any computer. And then the other one that we'll use a little bit here is Dr. Java. And that's also a free thing where you can download it for Mac or Windows. Before you run it, though, you have to download Java. So this doesn't actually have Java. This is like a interface to compile Java programs, and so you would have had to get Java from the other link first before you do the Dr. Java. And then here's just some other stuff that you could check out. Okay, so are there any questions about how the class is organized and what's going on? Okay, so what I've got next is some intro stuff about what's going on in the big picture. So most of this stuff, there won't really be test questions on or anything. It's just kind of give you an idea about what's happening when you're writing these programs and a little bit how the computer is organized. So kind of background material. So let's give an intro to about computing and programming, and then Java, a little more specifically on Java. So this is like a diagram that kind of corresponds to those different levels for grading. And the idea is it sort of depicts sort of like an onion with different layers here. And it shows that the kind of the foundation are data types. And data types are essentially what fundamentally you can manipulate in the computer. And after you understand data types, then you can build on to that with variables and expressions. And then after you understand variables and expressions, you can build on and do iteration. That's where you just repeat stuff over and over again. And then control structures, that's just a fancy term for doing like a branch in a flowchart. So if something is true, then do this thing, otherwise do something else. And then on top of that, you have fancier things like breaking your program up into methods, using classes and arrays and so forth. So that's kind of the approach we're taking as we're sort of starting from the innards and working our way out to the top. There are some people that are taking a different, like a top-down approach, where they actually do this stuff first and then work their way down, which is a little unusual. But so I'm sticking to the more traditional approach of learning the simple stuff and then building on from there. Okay, so once again, this is one of the reasons why I'm trying to do this different levels of grading thing, because if you don't really understand data types and variables very well, then you're going to be pretty hopelessly lost on arrays and classes. So you'll have an incentive to try to focus on this earlier stuff to get it right. All right, I mentioned this as well, and so kind of the design here is not to just recite what's in the book, but cover the same concepts with some different examples, and lots of programming activities. And so the other kind of philosophy is programming is kind of like learning to play a musical instrument. You know, there are a few rare people that can listen to me say stuff about it and then they can just instantly go and just write programs. But for most people, you have to like practice and try things and stuff doesn't work and then you try it again and figure out how to make it work. And so it's this cycle where you repeatedly try things. So don't be discouraged when your programs don't work. And so like 95% of programming is like failing. And then it's when you get it working, you know, that 5% is the rest of it. So there's going to be lots of cases where your program doesn't work, and that's pretty normal. You know, it happens to the best professional programmers. Almost nobody gets it right the first time or the second time. So expect to do lots of different attempts at programming. The one thing you shouldn't do, though, is if you ever get to the point where you feel like you're just guessing, because you'll have this code in front of you and you might think, oh, if I change this to that, maybe it'll work. If you get to that point where you're just randomly trying stuff, then that's where you might be in trouble. So at that point, you should probably step back and then reread the material or talk to me or something, because your chances of success when you start randomly trying stuff are not very good. I guess maybe the irony there is the very first simple programs, you can actually do the random thing. So it might encourage you at first because it's going to work initially when they're pretty simple. But when you get to slightly more complicated programs, then just sort of trying stuff is not going to work. Okay. So let's give a little introduction to what computing is. So what's happening when you're writing a program and running a program. So here's like a diagram of basic parts inside a computer. So if we opened up one of these computers, you would see a chip that's got the central processing unit, so that's the brains, so to speak, of the computer that makes all the decisions. All these lines over here are called the bus, and the bus is basically a bunch of wires that connect different components inside the computer. Another section is your main memory, and so nowadays you'd have whatever 2 to 8 to 16 gigabytes of memory. The bus also connects other things that connect to the computer, like the hard drive or your video or the network, for example, or USB. So all that's connected through the bus, and you can have multiple different buses in most computers. So that's like a pretty simple picture of a typical computer. One of the challenges now is we're sending so much data between the central processing unit and memory and the video. So now we have this HD video, and you might have some game or something that's running huge number of pixels on the screen, and you want it to be really fast because maybe it's supposed to be some fluid, real, visual, realistic looking thing. When we do the math, there's actually billions of pieces of data that have to flow back and forth between memory and your video every second. And so having these buses that can handle that traffic is important today. So one of the things that's happening now is actually some of this video stuff is being put on the same circuit board as these things. All right, so I said a little bit about the CPU. The CPU is like the brain. So what the CPU does is it goes to main memory. Let me back up here. So main memory will contain your program. So the program is like a sequence of instructions that the computer should do. And so the CPU will go to main memory and fetch a instruction and actually carry it out, and then go back and fetch the next instruction and then carry it out. And the sequence of all those instructions is your program. And ultimately, all of that data is stored in ones and zeros. So, and then those ones and zeros would be pieced together to represent different things. So that's all in binary. You can think of main memory as just a big list of addresses. So some people make an analogy to like mailboxes on the street or something. So you have address 4802 and you can store some information there, and then you have the next address, you can store something there, and so forth. And if you have a gigabyte of memory, there'd be like a billion of these addresses. And then the things you can store in each address could be data values. So maybe I want to store the number 10, so there'd be a 10 hanging out here. Or maybe you want to store an instruction. And so there could be something in here that's an instruction that tells the computer something to do. Each one of these data values is like a fixed length, like maybe it's 32 bits or something. A bit's a 1 or a 0. And sometimes you want to store more than that, and so then all we would normally do is just use consecutive memory locations. So if I had something that, so let's say each one of these slots could store 32 bits. If I want something that takes 64 bits, then I'd just be using 2 of these slots back to back. So a bit is the smallest basic data item in a computer. It's a 0 or a 1. So it stands for binary digit, 0 or 1. And then a byte is a group of 8 bits. So here's 8 bits slammed together. And so now we're just mentioning gigabytes, so that'd be like billion bytes, and megabytes would be a million bytes, and so forth. And then sometimes you hear this term a word. A word is a grouping of 1 or more bytes, and then how many bytes depends on the computer. So nowadays generally mean like 8 or 16 bytes is a word. Let's see. So this just shows how we can make different patterns of bits to represent things. So if you have just one bit, 0 or 1, you could represent 2 things, like on or off. And then this is also generally used to represent true or false. So something that's true is usually 1, and something false would be 0. If you put together 2 bits, then here are the 4 different patterns you can make of 0, 0, 0, 1, 1, 0, 1, 1. So if you had 2 bits, you could use that to represent 4 different things. And so they could represent, for example, let's see here. So they could represent, you could make it so this represents the number 0. And you might have it, so this represents 1, that's 2, and that's 3. So if you had 2 bits, that would be enough storage space to represent 4 numbers, 0, 1, 2, and 3. And then if you have more bits, like 3 bits over here, then now here you can see there's 8 different patterns. And so now I could use this to represent 0, 1, 2, 3, 4, up to 7. And if I have 4 bits, I could go from 0 all the way up to 15. And if I had 5 bits, I can go 0 up to 31. So basically, the more bits we have, the bigger number we could represent. And so nowadays, we'll be up to like 32 or 64 bits to represent fairly large numbers. Let's see. Before I leave the slide, I don't have to make these bits represent numbers. I could make them represent whatever I want. And so I could also decide maybe maybe I'll have it so that this represents 0, and then this represents 0.1, and this represents 0.2 or something, and that's 0.3, etc. And I could make it so this represents, I don't know, 1.9. So I could pick my own things that these represent. So it's kind of up to us, and that's this idea of a data type. Inside the computer, you just have these 1s and 0s. But how you interpret those 1s and 0s is what the purpose of a data type is. So I could make them be integer numbers, floating point numbers like this, or I could even decide there's something totally different. Like I could decide, all right, this is going to be the letter A, this is going to be B, and this is going to be, I can do, because I don't need 32 of them, but whatever, this could be exclamation mark or something. Okay. I've mentioned these already. I'm sure you've seen these terms around. So a byte is 8 bits, and so these are represented as powers of 2, and so a byte is 1 byte. A kilobyte, most people think is exactly 1,000 bytes, but technically it's not. It's really 2 to the 10th power of bytes, and so really that's 1,024 bytes is a kilobyte. And same thing for a megabyte. It's 2 to the 20th, so it's really 1,048,576 bytes. And gigabytes really a little over a billion, and then a terabyte's whatever that is, trillions. So I already mentioned this, that bits could represent characters. So here are actual values from what's called the ASCII code, the American Standard Code for Information Interchange. So there's this code that people have agreed to, where if you see the, if I back up, if you see the pattern of bits that would be the number 72, then in the ASCII code, everyone's decided that's going to be a capital H. And if you see the number 46, then that's going to be the code for a period. So whenever you're typing in your word processor or whatever, anytime you're typing letters, basically, anytime you type capital H, basically the bit code for that corresponds to 72 is being stored somewhere in your computer. You could even have these things represent other things like sound or images. So a pattern of bits like 0001, 0001 could represent, say, a sound wave. So you might wonder, how could that represent a sound wave? So when you have a sound wave and you have something making sound, then the way you hear that sound is you've got all these air molecules over here. And then as you say something, the molecules get like a little compressed. And so you have these compressions of air molecules. And then you pick up those compressions with the microphone. And so if you plot it over time, it might look something like this, where here they were really compressed and then they were not compressed and got more compressed. So this would be, this is kind of like a sine wave. So you would really only see this if you had like some pure kind of tone happening. But this would be the compressions of the air, and you could represent it. This represents the sound. And so the idea is, you could turn this into numbers, so where you could say, all right, this is like 0, maybe this, let's go back here. Maybe we'd say this is 0, and up here at the top, that would be maybe 255. And so we would take samples at different times, so maybe this is 170, and another sample here, that's like 5, and up here, maybe it's 230. Another one over here. So what we do is we would take a sample of the sound wave at different points, and hopefully we have samples at enough points that you could get an accurate reproduction of the sound wave. That's pretty close. And so now we just have like a big list of numbers, and that big list of numbers is what gets stored and then would represent the sound wave. Yeah?
Is that kind of like for lower quality audio, maybe they're just taking less samples?
Exactly. Yeah, that's right. And so if you have a low quality, if you want to have a really low quality but not taking up very much space recording, then you would have fewer of these samples. And if you want like a really high fidelity sampling, you would have a lot more of these, and it would take up a lot more space. There's a point where if you take up too many of them, it doesn't matter, because your human ear can't tell the difference between a sample of 1 microsecond apart. So there's a point where it's just wasted space, but okay, so here's the picture. I was getting ahead of myself, where you'd sample at different times. And then you could have bits represent colors. And so here's an actual color chart from somewhere. I guess this is not maybe that standard, but you could have it so this would be like a color palette. And you could say, all right, anytime you see a number 0, that means it's white. A number 1 would be a black. Whatever this is, 185 is kind of orange. And so if you wanted to transmit a little picture where it had a black here and then a white and then a black, and then maybe if I do it like this. So if this was our picture we wanted to send, where you had a black, white, black, white, 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 black, white, black, then you could transmit this as like black was first. So if we go like in this order, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you could basically transmit the numbers 1, 0, 0, 0, 0, 0, 1, whoops, 1, 0, 1. You could transmit this, and this would say, well, the first pixel or color here should be black, so that's a 1. Then there's a white, so that's a 0. Then there's a 1 for the black. Then they had 3 whites, and then 1 black, and 2 whites. So put these together and you could transmit some kind of image. So we'll do some stuff where we do some manipulation of pictures later on. So we see that bits could represent colors, sound, numbers, and they can also represent instructions for the computer. And so this would be the job of the designer of the computer chip. So whatever, someone that's working for Intel or AMD or whatever. And so they would decide that, okay, I'm going to make it up so that the sequence of bits 110, 110, that's going to be my instruction for the CPU to add 2 numbers together. And then maybe the person decides, all right, this is going to be the sequence of bits for the instruction to add 1 to a number. So when you add 1, it's incrementing a number. And so this is called binary code. And it used to be in the olden days, the programmers would write their programs directly using binary code. And originally it was done using switches. And so imagine standing in front of this console and having a panel of switches. And if you wanted to enter the add instruction, you'd flip 2 switches up, 1 down, next 2 up, the next 1 down, and you push a button, and then that would go into the system as your first instruction, and then you do that for the next one. So it was very tedious to write programs this way. And nowadays, if you're writing at this level, which is kind of unusual actually, but if you were, then we have a thing called assembly code, which is 1 step up. In assembly code, you have kind of a more meaningful sequence of letters, mnemonic, to associate with the code. So there's a code like add.d, that's like to add as a double. And then you could give it the things you want to add, and then you would write your program like this, and then there'd be a program that would translate that into the binary code for you. I had briefly mentioned this before, but all the CPU is doing all the time is it's running this thing, the fetch, decode, execute cycle. So the CPU is just sitting there, and then it goes and gets an instruction from memory. It decodes it and figures out what that instruction is, and then it goes to the next place in memory. It figures out what the instruction is and executes it, and then it goes to the next place in memory and then gets to the next instruction. So even when your computer is sitting there at the wait screen, waiting for you to log in, it's still doing this cycle. It's getting some instruction, running it, getting another instruction, running it. So the instruction might be to just do nothing, but it's still doing something. Actually, it's doing all sorts of things in the background. Okay, so at the bottom level, we said the computer understands these 1s and 0s to run a program. I had briefly mentioned this thing, assembly language, where you can write in slightly higher level, where at least you don't have to know all the 1s and 0s. You can memorize a instruction like LD for load the accumulator, and then this would be translated into the 1s and 0s. And then what we're doing, though, is we're writing in a high-level language, and so we can write in much more abstract ways, a little more English-like, really more logic-like. So we could write things like A plus B to add A and B together, maybe, and then that would be translated into the 1s and 0s for us. So we're bypassing this stuff and bypassing that, and we're focusing all our time on the high level. So to do this, there's a program called a compiler, and we'll be writing this code over here, and then using the compiler, which is a program that takes this code we wrote, and then it'll translate it into the machine code that the computer can run. There's another model called interpretation, and the way that interpreters work is you have some code here for your program, like set x to 3 and set x to itself plus 1. And rather than compiling it into a bunch of machine code all at once, the interpreter can take this code. The interpreter can take like a little chunk of the code. Maybe it just takes this 1 line. And then that 1 line gets turned into machine code, which is executed. And then we go back and then get the next line and then go and turn that into machine code and execute it and so forth. So the difference with interpretation and compilation is back over here. This would be your whole program. You compile it once to machine code and then just keep running it in machine code. If you did the interpreter idea, you're constantly kind of compiling. It's like compiling your code all the time. to run your program. So for example, an example of an interpreted language would be like if you start your web browser and you're doing something in JavaScript, yeah, that's probably a good example. So imagine you go to some web page and it's got some stuff in there where you can do stuff kind of in real time on the web page. This is actually running a program like this, where when you went to the website, you downloaded the source code, and then your web browser started running it. And then the compilation model is more like what you do with a regular program. You download it, and it's like file.exe, and you run that program, and it just goes. So why am I mentioning these two things? Is because Java is the language for the class, and Java has components of being both interpreted and compiled. And that's a little bit of a simplification for today's compilers, but we won't really worry about that. So the idea is someone writes some code in Java like this. So here's some program that does something. We'll use a Java compiler once, and then it's compiled into this machine code. On a normal computer, your CPU could directly run that code, but Java is a little weird. This is machine code that would run on what's called a Java virtual machine. So kind of like it sounds, it's a machine that doesn't really exist, but, well, some of them do exist just as a curiosity. But generally, there's not an actual computer that can understand this machine code, but there's a hypothetical computer that could understand it if it was created. That's this Java virtual machine. And so that might seem a little weird. Why would you compile to machine code for a machine that doesn't actually exist in real life? And well, the reason is it's compiled to this machine code that from that code it's pretty easy to make it run on other computers. And so with just like a pretty short step, you can take another program like on a Mac or a PC that can take this code and then translate it to native Mac code or native Windows code or whatever. So to actually run the Java code, you need to have the right interpreter on a PC or Mac or Linux, or I put Palm Pilot. That's, you don't see those anymore. How about like Android or something? So it's pretty easy to go from this Java virtual machine to all these other different devices. And that's the philosophy behind making Java in the first place. The theory is you could write your program once over here, and then you can run it on all these other machines. So you write it once, you can run it on PCs and Macs and Xboxes and whatever, and cell phones. And to some degree it's kind of true, but not totally, because these interpreters tend to not have all quite the same features. So, you know, on your phone you might not be able to do the same thing that your PC can do. But it's mostly true between Macs and PCs, though. Okay, so that's like the big picture about kind of all these things that are happening behind the scenes when you compile and run a Java program. So if I back up a little bit, so you know, here we go through this process to compile the Java program, but then to run it, we have to use this interpreter thing that can take this code, translate it to your native machine code. So there's a whole bunch of stuff that's happening in the background. All that's kind of hidden from you. Like when you're using one of these IDEs, all you do is you just push a button, and then all the stuff happens for you automatically. But so it's nice to know a little bit of what's going on behind the scenes. Okay, so for you, when you're writing your programs, you're trying to figure out the list of instructions for the computer to follow. And part of that is just learning what instructions there are and what they look like and how to type them in. But then the other part is programming is really lots of problem solving. And so it's a lot like solving a puzzle. I'm trying to figure out how to piece together the right instructions to actually solve your problem. So for example, here's a typical problem that we do is you have a list of something and you want to search the list for a value. In this case, I got a list of names, and maybe you want to search the name to find the person's phone number. So you want to know what's Karaoke's phone number. So we have a couple ways we could solve this. So I guess if you were doing this, how would you, as a human, how would you, if you're given this list, it's pretty short, I guess, so you probably just look at them in order. So what strategies might you think of to find the phone number for a given name? So anyone want to throw something out there? So just if I just asked you right now, what's karaoke's phone number, how would you figure it out? You just look for it? Yeah. But so if we break that down, like how, like did you use an order? Start. So I get, in this case it's a little weird because it's so short it just pops out at you. But what if this was longer? What if there were, 100 names or something? So you mentioned you just start at the top. And so that would be one strategy you could use, is you could just start at the very first name and check, is it karaoke? No. Go to the next name, is it karaoke? No. And just keep on going. And that would work pretty well for, computers are fast. They can just zip through that whole list in an order like that really quickly. But any other ideas? What if this was even bigger though, like, phone book sized or something? You jump to the O's? Yeah, and so if there was like some kind of index on it, then you could skip some of them. So here, it's alphabetically sorted. And so what if you had no index? What if you knew it was alphabetical, but you didn't have like letters on there? So like a phone book, what would you normally do if you're looking for a name in the phone book and it doesn't have tabs or something?
Just flip to a random spot and see how far into the alphabet I am, and then backtrack and go forward.
Yeah, exactly. So you could do the same thing here. If you wanted to be a little more systematic, instead of just flipping to a random spot, then you might just start in the middle and then say, okay, I'm looking for karaoke. And I know that I flipped here and I got al dente, and I know that O comes after D. And since it's alphabetical, there's no way it could be any of the top half of this list. So it'd have to be somewhere in the bottom half. And then I could repeat the same process out of the bottom half, maybe flip right here to the middle. Maybe I get to Guini and say, oh, okay, it's still going to be bigger than G because it's an O, so I can ignore those. And then maybe out of the last two names, maybe we go check here, right, and say, okay, O comes before W, so it has to be before W but after G, so there's only one left. So there's a process we could use to try to narrow down the name. So this particular one is called binary search, and we'll talk about it later. But it turns out that binary search runs really fast because every single time you look at a name, you can cut the length of the list in half every time. So if you've done like the intermediate algebra class, then it'd be like logarithmic, and you take a logarithmic number of things you'd have to search based on the length of the list. So even if the list has millions of things, it'd only take like 20 or 30 checks to find the right name. So with programming, a lot of the challenge is coming up with the algorithm, like what approach we're going to use to solve the problem. So we could do binary search, or you might just do the simpler sequential search, just look through every single name till you get to the one you want to find. So what we'll typically do, or sometimes do, we tend not to do it for short programs, but for longer ones it's really helpful, is write what's called pseudocode. And so it's kind of like code, but not really. It's like a mixture of English and Java to figure out how to write the actual Java code. So here would be an example of pseudocode for the binary search idea. You might say, okay, given the list of names, assuming it's sorted alphabetically, if it's empty, then, well, the name you're looking for can't possibly be there because there are no names in the list. Otherwise, jump to the middle of the list. If it's the same, then you just found it. If it's alphabetically before, then repeat on the bottom, and then flip this if it's after. So if you kind of write this stuff down like this, then it should give you like a good framework to go and start actually writing the real code to implement your program. All right, so let's do like a really simple example. And then that's all I have for you to do on the drill is to basically do a similar thing where you enter and run a program. So there are lots of ways you can enter and run programs. The one we're using here is this thing, Dr. Java. And you can use others if you want. So really, you're free to use whatever Java program you want most of the time. There's a couple assignments where I'm going to ask you to use NetBeans specifically because there's some debugging stuff I want you to do. But in general, if you have some other way you'd like to write programs, like sometimes we've used TextPad in the past, or if you're done other stuff and you like to write them using whatever Emacs or VI or whatever, you can use any environment you like mostly. Okay, so when we make a Java program, it's usually in a file that's called .java. And here I'm just going to right-click and make a new, sometimes I'll do this, I'll make like a new text document and then call it something like program.java and get rid of the .text. So our program should be in this format where it has the name of the program, a dot, and then Java is the suffix. And you have to be a little careful on these machines because I think the default for these is it hides the suffix. So like you'll see on all these, I have .html, .xls, .doc. But I think the default for all these is to hide the file name extensions. So it might just look like this. So here it just says program without the .java, but it's really there, it's just hidden. And so the mistake that sometimes people make is they call them .java like this. So if you have the file extensions hidden and you put in like the .java, then if I unhide them, then here I really renamed it to program.java.java. Because it already had the extension there in the first place. And so anyways, you can get in trouble if the extensions aren't being shown. So I would recommend just always showing the file extensions. And I'm on Windows 8. Oops. I'm here on Windows 8, and so on Windows 8 there's like a checkbox for it right here in the File Explorer. But I think on Windows 7 you have to go to like View Folder Options or something, and there's a checkbox to turn on or off. So it's a little different under Windows 7, but it's somewhere in like the View Options menu. It might be in here, let's see. Yeah, so it'd be like in folder options, and then there's this check radio button here for show hidden. No, it's not that one. It's to uncheck this one for hide extensions for known file types. So I'd say probably turn that one off. So if you have a .java file to start with, then usually you can right-click it and say open with like dr Java. The other way you can do it is you could start dr Java first or Dr. Java first. Where is it? I had a shortcut to it somewhere. Where'd it go? Oh, it's right here. So it's this thing that looks like a J, and I guess on yours it should be somewhere in the start menu. Has anyone actually been able to log in and start Dr. Java?
I don't think we have it.
It's on the computer, you just have to go to that shiny button on the
Yeah, it's there. You just
If you
search
go to all
with it on the menu,
programs,
and
and
search
go
with
through the list of programs and all programs that we do.
Okay, yeah, thanks. So it's in there. So, so you can start it up, and it should look something like this. And if you have an existing program, you could just open it up by finding it, or you can just go and drag it in. So like this guy could just drag in there. And well, there's nothing in it right now, so if there was something in there, you'd see it show up, but right now it's an empty file. Okay, so what did I want to do here? I was just doing a Hello World program. So it's kind of a tradition to have like a first program just prints out Hello World. So we'll do a similar thing here. So one thing you can do is you can add comments in your program. Comments are like how you would describe what the program does. You could put your name. So basically, the computer's going to ignore everything that's in comments. So you have two ways you can make comments in Java. I can do a slash and a asterisk. And then everything I type in here will be ignored until we get to a asterisk followed by a slash. So normally you would put a description of the program here. You could put your name, date, anything else you find you would want to add there. And then when you're done with comments, you do a */, right, like that. And so this says, here's where the comment begins, and then over here is where the comment ends. So one nice thing that this program does for us, this Dr. Java program does, that you'll notice here, is when I did the /*, it puts these stars in front for me. You don't really need them there, but it just does that so it looks kind of neat to really show here's where your comment is. If I was using like a program like Notepad or something, then it wouldn't be adding this stuff for me. It also wouldn't be making it green, and so it does some color coding for us as well. Okay, the next thing we do is we have the word public, the word class, and I'm going to call this Java program. So here's like the highest level sort of template we'd have is the word public, and we'll say more about what all this means later, but for now you just do it because that's what you need to do to make a program work. The word public, the word class, and then this next thing though, Java program, you get to pick what this is, but whatever you pick here has a few restrictions. I'll add a comment here. The program name must start with a letter. Normally it's uppercase. It doesn't have to be uppercase, but that's like the convention to make the first letter uppercase. It could contain digits or an underscore, but not other characters, and no spaces. So here I just, usually it's just all letters, so here I called it Java program. The other normal convention is if you have sort of two words squished into one, then you make the second word be uppercase for its first letter. But once again, you don't have to do that. I could make them all uppercase or all lowercase, but if you want to conform to the standards of Java programming, then you would do it this way. Okay, so once we've picked a name for this, and so typical names you might pick would be like, program 1 or homework 3 or whatever. Whatever name you pick, it has to be saved in a file with the same name with a .java suffix. And so what I would typically do would be to go up and go like save as, and then here I had called it Java program, and so it should be in a file that's called Java program.java. If you pick a different name, then it might not work correctly. There are some cases where it will work, but others where it won't. So the safe thing is just make sure this has the same exact name here in your code and the file name. So I'll save that. The next thing to do is you have to have this thing called a method. And this is the main method, and it looks like this. You have the word public, static, void, main, string, square brackets, and then args, and then more braces. These are curly braces over here, not parentheses, in case it's hard to see. So for now, this is also just more weird looking stuff, but yeah, you have to have one of these for every Java program. So basically this is saying it's, what public means is open to the public, anyone can see it. Static means there's only one copy of it. Void means it doesn't return anything. Main means that this is where your program starts running. And then this thing over here is an array of strings, and we'll talk about that later, but that's a way you can send in arguments to the program so it has data to work on. So as far as like a template goes for starting your first, well, really for all your Java programs, you could start with this, and for now you don't really need to worry about what these things are saying. Okay, so inside these curly braces is where your program starts. And so we'll start by just outputting something. To output something, I can type in system.out.println, and then parentheses, and then double quotes, hello world. So this is saying go to system.out, which is the console for where you would see output from the screen. Print line says to print one line, and then inside parentheses would be the thing we want to print. And in this case, we're going to be printing out hello world. When you have a string of characters you want to print, they have to be inside double quotation marks. So make sure it's double quotes, not single quotes. And then every line of code that does some execution has to have a semicolon at the end. And so it's a little bit of a learning curve to figure out where your semicolons go and where they don't. But so for example, a semicolon does go there, but a semicolon doesn't go here. So anyways, you'll pick it up as you go along where the semicolons belong. Okay, another kind of comment we can make is we can put 2 slashes, and then anything from the slashes to the end of the line is ignored. So these are called inline comments, because normally you would put these comments to describe something about the line they're on. So for example, I might put a / right here and say the name, in this case Java program, must be in a file named javaprogram.java. So anything from the 2 slashes to the end of the line is ignored. So this is another nice thing about this Dr. Java thing, is it puts all the comments in green for us so we can see what are comments. There are some of these special keywords like public and class, and it puts them in blue, and then other stuff is in black. And here we can see the string here is in red. This hello world's in red is called a string. Sometimes I'll do things like forget to put an end quote, and then with the color coding of this thing, that it makes you see really quickly, oh, you know, this stuff is all red, so it means I must have forgotten to put the double quote somewhere, and whoops, that can go away. So I add the double quotes back, and the color coding gets fixed. Okay, so when we're at a point where we're ready to run our program, then here I'll save it, and then to run it, click over here on compile, and down here, this program's so short it compiles pretty instantly. If I didn't have any errors, that it says compilation completed, and then to run it, I can click this run button over here, and what happened there? Working, oops, I got something funky with mine. I should be able to click there and run it. You can probably click there and run it. I think it's just it should just be my computer where it's got issues. Oh, let's see here. So I'm gonna so it should work for you guys, but I ought to fix my computer. I have like different versions of Java on here, and so what's going on with me is it's compiling it. Well, maybe I can do it over here. I got rid of it. So my problem is I have different versions of Java on here, so it's trying to compile it in one version but run it in a different version. But it should be okay for you guys. So anyway, you should be able to click here and say run. When it runs, then you should see it print out hello world down there. So I'll get mine fixed for next time. Let's see. Okay, so any questions about what we've just done? Okay, so I just had a few more slides to cruise through, and then I'm done, and then I'll let you do the little drill thing, which you might be done with already because it was basically what we just went through. So the last part here is I had some questions for you. Here's like a little mini quiz. So anyone have the answer? What is pseudocode? That's right, yeah. So it's a mixture of like English and programming code, like Java, with the goal of getting you from your brain's idea of what's going on to the actual programming code. It's kind of an intermediate step. And here's like a totally different question. Back to the very beginning where we talked about what we could do. So what activities are okay to work with others, and what should you do by yourselves? That's right, and you can talk to other people at homework, but not like, copy the assignments. Okay, so with that said, what I've got is back up here on the calendar page. Oops, I shouldn't have closed Blackboard. On the calendar page for drill number 0, all I have you doing is making a hello world program that, in this case, call it hello world. So your file should be called hello world.java, and then have it add onto it so that it says hello world from, and then prints out your name. And it could all be on the same line. So if your name is Bill, it would say hello world from Bill. And then just show me your program, and then we're done for today. And before tomorrow's class, if you can go back to the calendar page and see what we're going to be covering and look at what the drill is in advance, that'll make it go a little bit faster. And in fact, if you wanted to, you could do this in advance, and you could just show it to me when you come in here, or you could just email it or whatever. Okay, so any questions? Otherwise, I'll start coming around whenever you've got the program working, and I'll mark you off. Okay, great.